Hi everyone, welcome to last theory lunch of this semester. We have Majid here to talk about on hardness and approximations of submodular minimum linear ordering problem. And this idea is sponsored in part by Smart Contact Research Forum. Yeah, Majid.
Thank you, Professor. So this is a joint work with my colleagues at Georgia Tech and my advisor, Professor Tatali, who is in the math department. We may also touch another work with Nikhil Bansal and Jatin Batra and Professor Tatali as well. But it's going to be mainly based on this work. So what are minimum linear ordering problems? In classical optimization problems, we want to minimize a function over, for example, subsets of a set. And as we will see, minimum linear ordering is a very natural counterpart to that. For example, imagine we want to minimize, we have a source and destination, and we want to minimize the cut function. So that's a polynomially solvable classical problem. What if we want to minimize the cut function over all prefixes of an ordering of the vertices? So the classical minimum cut problem wants to put some vertices here, some vertices there, and minimize the number of these edges. But the minimum linear ordering counterpart, so can this also be seen in the video?
No.
No? So the minimum linear ordering counterpart is summing is summing that cut function over all these prefixes. So it's going to count the number of edges passing here. It's going to then count the number of edges crossing this cut, and summed over all prefixes. So this is a very famous problem known as minimum linear arrangement. Why? Because each edge is going to be contributed to the amount of absolute value between its endpoints. For example, if an edge is between this vertex and this vertex, it's going to contribute to all these cuts. And the total stretch of edges is going to be minimized. So this is minimum linear arrangement problem. And as we will see, there are variants for the minimum sum problem versus minimum sum, versus the MLOP variance of them. So officially, we define the problem as given a function f, that is a cost function, and we are going to minimize f summed over all prefixes of an order. And so this is the notation in which we mean the first I elements in the ordering sigma. And it was introduced to generalize some previously studied problems by Iwata et al. For example, the minimum linear arrangement that we mentioned, minimum sum vertex cover, and minimum latency set cover that we will mention as examples. And it captures some arrangement problems. For example, it is closely related to scheduling problems. In what order should we make a set of actions instead of just choosing which actions to take? And because it's a apparently classical and abstract problem, the first two things to study are going to be when f is submodular or supermodular. And by symmetric, we are going to mean the function is equal when complementing a subset. For example, the cut function is symmetric. And submodularity, just to recall, means that intuitively it means that the more we have, the less we gain by adding more elements. So the other type of inequality that is equivalent to this that I like more is if we have a set and we have two new elements, A and B, adding A to the set increases the function more than adding B and then adding A. Just comparing the increase in the function due to adding A. So we just saw the minimum linear arrangement problem is equivalent when f is the cost function. So that problem is also referred to as optimal linear arrangement. It is hard, but polynomial time for trees. And in general, the best approximation is due to Feige and Lee from 2007. And note that we have a symmetric submodular function that is the cut function for this MLOP. So this is the first interesting open problem. Can MLOP for symmetric submodular problems be approximated? Not much worse than this. And there are currently no non-trivial bounds for that. So, and in the middle of the talk, I will mention some of the interesting open problems. Feel free to jump in. We can discuss over them. It's not going to be all about the talk today. Hopefully, we may get some time to discuss some new directions. Another example is minimum sum vertex cover. What is this problem? It is, again, ordering the vertices of a graph, and each edge is going to be satisfied or covered at some time. So think of the ordering as time steps. We want to label vertices, and an edge is covered at the time where one of its endpoints is appeared in the order. So the cost due to this edge is minimum of sigma of u and sigma of v if u and v are endpoints of that edge. And this is going to be summed over all edges. So this is the minimum sum vertex cover. That is the counterpart to vertex cover. And if instead of edges, we have hyper edges, I mean subsets of large size potentially larger than 2, it's going to be minimum sum set cover. And if instead of this mean, we are taking the max, it's going to be minimum sum latency, minimum vertex latency cover, or minimum latency vertex cover. So the mean sum vertex cover, that is for the mean case, is shown to be not having a p-test. Its best approximation was a 2-factor or close to 2 since early 2000s. And we recently improved it with Nikhil Bansal and Jati Matra and Prasad Tatali to 16/9. That I gave a talk last semester on that, in which we discussed kernel alpha point rounding. So these are some classical problems that are all MLOPs. As we mentioned, for symmetric submodular, the most interesting is MLA. Sum cut is also an interesting problem that we don't talk about. Multiple intents ranking used in search engines is one of the problems from the 2000s that was designed to increase the diversity in the search results, or it can be thought as minimizing the expected cover time of the unknown intent due to a search result that we do not talk about. Minimum sum vertex cover is also a problem we do not talk about, but just to mention that it's a special case of minimum sum set cover, where instead of an edge, we have a hyper edge, and that is a supermodular MLOP. So Iwata et al. Showed that supermodular MLOP is for approximable using the same algorithm that Tatali et al. That Feigelovash and Tatali provided. And it is interesting that this case is concluded because they also showed that minimum sum set cover is not approximable better than a factor of 4. So that case is concluded. But the submodular case is further open. And we are going to mainly talk about monotonic submodular MLOPs, where that submodular function f is non-decreasing and non-negative. And some special cases of the functions that are monotonic and submodular are rank of a matroid or rank of a graphic matroid that we're going to see. But the first thing is to further characterize and even check whether these special cases are even NP-hard.
Sorry, a question
Please.
on that. So something like minimum latency vertex cover or
Mhm.
minimum latency set cover, are those not monotonic?
Minimum,
It's like minimum latency set cover. Is that not a monotonic function? Or is it a negative? Like it doesn't seem like it's negative.
so we need to formulate it as an MLOP. So let's think about how we can formulate mean latency vertex cover as an MLOP. So it's going to minimize the maximum of the endpoint.
That's what we're gonna end up.
But what is that function f? We need to formulate it as minimum overall permutations, summation over all prefixes, that function over the first I element. So I would say,
Oh, so we negate everything.
yes. So one way to formulate this problem is to see that for a given permutation, each edge is covered at the last time where its endpoint is appearing in the ordering. So one way to define the cost function is to say, let's look at the suffixes. As long as this edge is not neighbor to a suffix, it is not going to be penalized. So we can say it is going to be penalized n times minus the number of times it is not in a suffix. So what is that? Let's say for a set V, F is, or G is the number of edges that are adjacent to that set, not the induced graph. So it can be formulated as something like n. So the objective is going to be the number of edges times n minus that summation of the function over suffixes. But suffixes and prefixes are symmetric, so it doesn't matter which way we think of it. So that function is aggregated over suffixes and is negated. So it is not exactly formulable as a function f. And it is neither, not even submodular probably. Because maybe it's a negative of a submodular function, but it's going to be then supermodular, but it's also added by value. So I don't recall whether, yeah, so maybe we can show that it's submodular because of that function of the number of edges that are adjacent to vertex. But I don't know whether I got your question at the beginning.
Yes, what I wanted to figure out is minimum latency set cover monotone? And the answer is no, it's not, because you have to formulate it with this thing.
Oh, okay, thanks. So let's define those special cases that we are going to talk about for the monotone submodular. What was a matroid? A matroid is a monotone submodular, can be defined as a monotone submodular function that is further upper bounded by the size of a set for each subset of the elements. And that function is called the rank of a matrix. Maximal, so independent sets are defined those that achieve the maximum value of the function, and minimal dependent sets are those that adding one more element does not increase the function beyond that value of the set size, and they are called the circuits. So one special case of a rank function for the matroid is to look at a graphic matroid. And then these independent and dependent sets would resemble forests and subgraphs that have cycle. But let's first quickly see that the problem when F is rank of a matroid is NP-hard. So a special matroid is defined by a matrix where the function over each subset of the rows is going to be the number of independent rows of the matrix, linearly independent. And a problem on matroids that is known to be NP-hard is to check whether the matroid is the same as the uniform matroid. And uniform matroid is to define the function for each subset as the minimum of its size and k. So the independent sets are all those of size, all subsets of size k for that matroid. So let's see why the uniform matroid isomorphism is equivalent to so let's see why computing the MLOP for rank function is at least as hard as the uniform matrix isomorphism. So we give that matrix, we give that rank matrix of the problem as an oracle to the MLOP, and if it is a uniform matroid, then MLOP objective value can be calculated because, as we will see, the MLOP is going to pick the ordering such that it is not increasing the rank as soon as possible. But let's not get into details of that because it's easy. So it's harder to show. Special cases are hard. So a special case of the matroid is when we have a graphic matroid. So our function is rank of the graphic matroid, that is size of the spanning forest of maximum spanning forest of the subset of edges. And we are going to note that we are going to order edges, thinking of the minimum linear ordering problem. And because the rank function for the graphic matroid is defined over subsets of edges. So, and note that if we show this special case is hard, it is something stronger than showing matroid MLOP is NP-hard because it is a strict subset of the problem. So how do we show that? Let's observe that, let's look at what happens to the graphic matroid. We are going to order the edges such that the function over them summed over all prefixes is minimized. So intuitively, we have a function that is monotonically increasing, and its value summed over all prefixes is going to be minimized. So it is better to prevent an increase and make it look like this rather than this. So what is going to happen for the graphic matroid is when we pick a when we put an index, when we pick an edge at index 1, and we pick another edge at index 2, it is reasonable to immediately pick the next edge that falls, that is connected by the farthest picked so far. So this is going to be costing us a value of 2. And if we have another edge there, we pick this, we make the function to cost the value of 3 for the edges picked so far, then this is going to be the next edge in the ordering. So is this clear? Because I want to mention an open problem here then. So we have, so we don't, imagine the graph is connected. Then the problem is to choose in what order should we label a spanning tree of it. So we don't know the spanning tree because here that spanning tree is this. And we said, let's pick this first and that edge and then this edge. And the cost of all other edges are uniquely determined using that. So the minimization problem is going to be over both spanning trees and then how to label them. And even if we fix that tree, the problem would be potentially easier, but doesn't even have a 2 approximation. But let's get back to the MP hardness. So for the graphic Matroid, we can show that the minimization problem is over all trees, and then we need to pick the ordering of the edges. So what we do for a graphic Matroid is if we are given a graph, then we add another vertex. We add edges to all other vertices from that new vertex S. And then intuitively, this is going to make the optimal tree to be this star. And then the question becomes, in what order should we label the edges of this star? Because that star is intuitively better than if we had a path, because for all of the edges of the graph, they are going to be covered very soon. So what is this? What is the cover time of each of these edges? It is going to be the maximum label of the label of the endpoints connected by the label of the endpoints corresponding endpoints in the star. So the cost due to this edge is going to be maximum of those 2 labels. And then the objective value would be equivalent to minimizing the minimum latency vertex cover problem, where the objective is going to minimize over permutations, the summation of the maximum label of the endpoints. And we get the minimum latency vertex cover value if we are given the solution to the, if you are given the value of the MLOP for the graphic rank Matroid as a function. But that minimum latency vertex cover itself was not known to be hard. But the counterpart minimum some vertex cover in which we have minimum here over the endpoints of the edge was known to be hard. It is also known to be APX hard. So any ideas on what to do with it? How to relate these 2 problems? Before reading the rest of the slide. So are the two problems clear? Please ask question. In one problem, we want to, in both of the problems, we want to find an ordering of the vertices. The objective for one is sum over all edges, maximum of the label of the endpoints. For one is the minimum of the label of the endpoints. So looking at this example, the minimum for an edge here is this label 2, but the maximum is that 4. If instead of looking at prefixes, we were looking at suffixes, then the minimum for that would have been the maximum for this. So if we only make this observation and want to look at the same graph, then to get the objective value of one problem from the other, we need to have the graph to be regular. But the key is to look at the complement of the graph. So if you look at the complement graph, sum over the minimums and maximums is clearly the number of edges of is clearly calculable because all indices are contributing to the objective. Because the value is, for example, mean latency vertex cover of the complete graph. And then what we do with that equality is take the summation from left side on the complement graph to the right side, then minus max is going to be plus min of the minuses. Then let's add a value of n plus 1 to all those indices that we are looking at and subtract it as well. So these two cancel each other. And then this value, instead of an index from the suffix, can be looked at as of a prefix, it can be looked as an index of a suffix. But the point is that that max got converted to a min. So if we have a oracle that calculates minimum sum minimum latency vertex cover, we can get the answer for minimum sum vertex cover of the complement graph. So this gives the hardness problem, but it is not approximation preserving. So we don't know that whether the minimum latency vertex cover is as hard to approximate as minimum sum vertex cover. So as we mentioned, the minimum sum vertex cover approximation zeta real for that is 16 over 9. When we have mean, there is 16 over 9. But when we have max, we show that it is 4 over 3. So it is an easier problem based on state of the art, because for neither of them, not a good inapproximability result exists. Let me discuss these. Yes, and this is the part when I mentioned we add a point and connect it to everyone to connect MLVC with Matroid MLOP. So in general, maybe it helps to get, so in that original figure that was connecting the problems, we have shown that computing MLVC is equivalent to MSVC, and MLVC computation is also equivalent to the graphic Matroid MLOP. So all those problems, hardness is bidirectional. But what do we do for the approximation of minimum latency vertex cover? So one hint is that let's formulate the problem as a scheduling problem. Can you think of the problem as a scheduling problem? what are the jobs that we are scheduling. You can assign to your jobs duration and weights. And this is the max case.
Would it be that, we have one job
Mhm.
last like 1 unit long.
Mhm.
A job at another vertex can't run until all of its all of its edges, all of its neighbors.
Yeah, that's reasonable. So if an edge is adjacent to these two vertices, we will have a job that must be precedented by these two jobs. What should we put the duration of that? It depends what is the objective function of the scheduling problem. So the objective function for one of the most famous scheduling problems is min-sum scheduling with precedence constraints, which in scheduling literature is noted as this. I think it was W, something like that, where W is the weight of the job and F is the finish time. So we give weight 0 to these jobs that are corresponding to vertices, but we give a weight of 1 to the jobs that correspond to edges. But the duration of those is going to be 0. So let's see what happens. Technically, what the scheduling machine needs to do is to decide in what order to pick the vertices, because those are the ones that take time. The edges don't take any time. They will be immediately scheduled after its endpoints are scheduled by the machine. But they are going to penalize the function by the time they are covered. So is the scheduling problem clear? And for the scheduling problem with precedence constraints, there is a rich literature. One of the results that we can use here is by Amble et al. From 2011. So the scheduling problem has many two approximations, but there are parameterized algorithms for it that can give better than two approximation depending on the structure of this DAG. And by the way, Nikhil Vansal brought this to our notice. I myself didn't know much about scheduling literature. But what is this parameterization there? It is kind of so dimension of a DAG is defined as the minimum size of its linear orderings such that for each two non-comparable pairs, they are appeared in both orders. So these two are non-comparable. If we have a set of orderings like 1, 2, 3, or the other one is 2, 1, 3, such that 1 and 2 that are non-comparable appear in both orders, then the size of this number of orderings is going to be this dimension. What they defined, so the problem had 2 minus 2 over d plus 1, something like that approximation already. What Amble et al. How the way they improved the algorithm was to define a fractional dimension. And what is that fractional dimension? It allows you to have more orderings. So let's say T, but it requires you to have the non-comparable pairs to appear in both orders at least k times. And then they define the fractional dimension as T over K. If K equals 1, it is just a dimension of the deck. And so let's see what is the fractional dimension of this deck that we have here. Let's give a minute of thought on that. Yeah, it's something like 2 or 3. But what is a easy solution for that?
1/3 approximation, it should better be 3.
Yes. But a nice way to come up with, to show the existence of that is a randomized algorithm. So let's say we consider a random permutation of vertices, and if we show that the expected probability of one job to be scheduled before the other job is at least some value p, then the fractional dimension is 1 over p. And this randomized algorithm is to order the vertices at random and start scheduling the vertices. At each point, at each time, some edges may be valid to be scheduled if both their endpoints are already scheduled. Then add them to the pool of the jobs and pick them still at random. So this way we can lower bound the probability of each job appearing before the other one if they were not comparable. Because all the edges are between, it's like a bipartite deck. All the edges are between 2 sides. And that probability with this randomized ordering is 1/3. So that was our algorithm for minimum latency vertex cover. One open problem there is to look at it first to improve that 4/3 that we derived it pretty easily, and then to look at the problem where we fix a subtree or a maximal for where we fix the subtree. Let's say the graph is connected, and we still want to decide in what order to label those edges. That is the graphic Matroid problem. So let me remind what that problem was. The MLOP for a graphic Matroid is asking in what order should we schedule the edges. We showed that if there is a spanning star, then the MLOP, the optimal solution for the MLOP is going to schedule edges of that star and minimize the maximum of the endpoints over other edges. There, it became converted to minimum latency vertex cover. But let's look at the original MLOP with the graphic Matroid as the cost function. What if that tree is, so the problem is minimization over all subtrees and also over how we label the edges of the subtree. Let's say the tree is fixed. If it's star, it is as hard as the MLVC. What if it's the path? Even for that case, the problem is not quite behaving in a way to be solved easily. But now we talk about the general MLOP with submodular monotonic cost functions, and we give a new parameterized algorithm using the theory of principal partitions. I'm not measuring time. Okay. So let's quickly recall what are the principal partitions for a monotone submodular function. It is going to give us a unique partial ordering of the elements. So let's say subsets pi 0 to pi s, such that each pi I is the unique minimizer of this function, of this objective. F minus lambda times the number of elements of that X. And that lambda can be between lambda I and lambda I plus 1. Just to look at the definition, but I'm going to pictorially present that to get more intuition on that. But the previous best approximation was 2 minus 2 over the size of the matrix plus 1, and our approximation is going to be parameterized this way, where L is what we call the linearity of the cost function. That is going to be the cost function over the whole set divided by the maximum of its elements. And for special cases, it is going to give other parameters algorithms. It gives strictly better than to approximation. For example, if the graph is irregular for some constant d, and what we use is the principal partition. So because of the interest of time, I will skip the details of the proof. But what is this principal partition giving us? So first of all, the algorithm is going to be very easy. The previous two approximation was also easy, but using Loesch extension. This one is kind of a greedy algorithm. So we get the principal partition sets, and we use them for, we give the ordering, arbitrarily ordering vertices of each principal set, and then in the same order of the principal partition. And what we need to show is that the MLOP objective is not much larger than this. So one thing that is easy to show is that, so consider the points of the optimal solution. Consider the optimal ordering. It is going to give us a cost that is the value of the function over all prefixes for the set of elements it is picking. So this set of elements that the optimal solution is picking is potentially different than a set of, that the order of elements that the principal partition is giving us. So this element is different than this element. One thing that is easy to show is that those red points always are above the objective for, are always above the line for the principal partition. But the point is that we have the value of the principal partition for the prefixes only at these points. So the cost due to principal partition may go above those red lines in between. But what we can show is that those red dots, so the cost will not go above that triangle that we see here. And then we kind of can sandwich the cost of the solution with the lower bound and upper bound and give the parameterized solution. So just to mention, or maybe recall a few open problems, The MLE problem is generalizing submodular symmetric MLOPs. And that is the most interesting open problem. But MLVC or even MSVC in approximability is much less than the state-of-the-art approximation algorithms for them. So they are also interesting open problems. With this, I appreciate any questions.
There aren't any hardness approximation results for MLOP.
For MLOP, for example, submodular, exactly, that's interesting. Is it harder to approximate them?
No. Do we know this curve log n log n?
For MLA?
Yeah.
I don't think so. That's also not tight. So one plausible result would be to show symmetric submodular MLOP is harder than this to approximate. Or just any non-trivial approximation for it. Because using the monotonicity strongly simplified the problem. It makes it too approximable. But without the monotonicity, for example, for the cut function, it makes it that hard.
There aren't any questions, it's time.
Thank you.